So we have a conceptual pipeline of how we can relate heat fluxes and heat transfer rates and heat transfer coefficients to the physical properties that define a system that is sufficiently well described by something that looks like a flat plate surrounded by a uniform background flow. And rather than spending too much time talking about the conceptual pieces of this sort of thing, rather what we want to do is to actually apply the pipeline that we've created to actually solve a problem. So let's talk about what the problem is. So we have this 5 meter long flat plate at a temperature of 290 degree Kelvin that's immersed inside of this liquid that is flowing over the plate at a uniform speed of 2 meters per second. Now it's only uniform away from the plate. We already discussed that whenever this flow actually hits the surface of the plate changes what the flow looks like. But we already talked about that. This liquid far away from the plate has a temperature of 330 degrees Kelvin. And this liquid is sufficiently close to engine oil that we can describe it using material properties that we would expect for engine oil, at roughly these temperatures. So we can find its density, dynamic viscosity, thermal conductivity, and Prandtl number to be the following. And if you're wondering, have I written the Prandtl number down as a shortcut? Well, no. Remember that the Prandtl number is only a function of the material properties of the liquid. And so by extension, it is also a material property. So you can find it listed in tables the same way that you can find the density and the dynamic viscosity and the thermal conductivity. So putting it here doesn't really matter. So we have this physical setup, and the thing that we want to try to find is, what is the heat transfer rate per unit width through this plate, right? And when we say unit width, remember that I never talked about how wide the plate was. And so really, what I'm actually talking about is, what is the net heat transfer rate divided by the width of this plate, whatever it is. That's what this Q prime is, all right? So this Q prime is just Q divided by W, but we don't know what the W is. So can we find it? Well, sure. The important thing to note here, right, is that this net heat transfer rate per unit width is related to the net heat transfer rate. And so as a result, when we do our calculations, we have to make sure that we utilize a correlation that describes an average Nusselt number, right? Not a local Nusselt number, because we're calculating something that relates to the heat transfer that happens through the whole plate, not at a specific location. So what's the first thing that we have to do? The first thing that we have to do is and this is kind of a free step for us now, but always find the Prandtl number. So if you don't have the Prandtl number listed like we do here, make sure that you find the specific heat capacity, that you find the dynamic viscosity and the thermal conductivity of the liquid, and that you calculate what that Prandtl number is, okay? So the first step is to determine that this is our Prandtl number. Now there's some subtleties to this, some which we'll enter into later. If you're trying to find a Prandtl number off of a table, you may ask yourself, at what temperature do I find that Prandtl number? Do I look it up at 290 degrees Kelvin? Do I look it up at 330 degrees Kelvin? There's not a really good answer, especially if we were dealing with a problem where we didn't know one of these temperatures. So the idea is that if you know just one of the temperatures, you use whatever temperature you got. And if you are dealing with two temperatures, then you just use the average of both of them. Because hypothetically speaking, that is a good representation of what you expect the temperature to be in the relevant parts, right? Like not close to the plate, but not super far away from the liquid. That average is as good as we're going to get. So you just find the material properties of the object, not just the Prandtl number, but everything else at that temperature, which in this case would be about 310 K. But we have our Prandtl number. It's 3,400. It doesn't have any units. We pulled it from a table. So that's the first step. The second step is to calculate the Reynolds number. And here we have to start being very careful, because remember, now it starts to matter whether or not we are calculating a local quantity or an average quantity, all right? When we're calculating a local quantity, we use a Reynolds number that's defined off a specific location. When we define an average quantity, when we're looking for a net heat transfer rate or an average heat transfer coefficient or anything like that. We have to make sure that we use the whole length of the plate. And so the Reynolds number that we're going to calculate here is just rho times U infinity times L divided by mu, where this L is the 5 meters. And the U infinity is 2 meters per second, and the rho and the mu R is listed. So without actually having to do the algebra on camera, I can just tell you that the Reynolds number that you get by creating this calculation is approximately 34,722.22. Okay? It's roughly speaking the Reynolds number that you get. Is this number smaller or larger than 5 times 10 to the 5? Well, 5 times 10 to the 5, by the way, is 500,000. And this is certainly smaller than 500,000. This is smaller than 500,000. So clearly, the flow never transitions to turbulence anywhere on the plate. The flow is laminar everywhere. Okay? So that's a key thing to notice. So we're going to write that down because it will be useful for the next step. The next step, now that we have the Reynolds number and the Prandtl number, is to find the Nusselt number. Okay? And the only way that we can find the Nusselt number is via empirical correlations, right? There's no theoretical meaning, or at least no fundamental kind of like theoretical know-how that will tell us something about what the Nusselt number is as a function of the Reynolds number and the Prandtl number. We're just relying on decades of experiments that give us correlations, empirical correlations, that connect a Nusselt number to a Reynolds number and a Prandtl number under specific scenarios. So I've written down 4 of those correlations. And you might ask yourself, well, why on earth do we need 4? Can't we just use 1? Well, remember, it matters whether or not we are calculating a local or average Nusselt number, right? A local or average heat transfer coefficient, a net heat transfer rate or a heat flux. And it also matters whether or not the flow actually becomes laminar. Becomes turbulent. It's anywhere on the plate. Like, is the flow laminar the whole time? Or is there a specific point past which the flow will become turbulent? And those things matter. And so the 4 correlations that I've written down in order tell you the following. This first correlation is the correlation that you use to find a local Nusselt number in a location where you know that the flow is laminar. Okay? And you simply use the local Reynolds number. So you use the Reynolds number with the length scale being the x, the location from the leading edge at which you are analyzing the flow. And again, you have to make sure that the flow is laminar there, which you can always check by calculating that local Reynolds number and seeing if it's larger or smaller than 5 times 10 to the 5. This correlation you use to calculate the local Nusselt number if the flow is turbulent. So if that local Reynolds number is larger than 500,000, then you use this correlation. This correlation is the one that you use when the flow is laminar everywhere over the surface of this plate, and you are trying to calculate the average Nusselt number, which is connected to the net heat transfer rate. And so the flow is laminar everywhere in our case, and we are calculating an average quantity or a net quantity, and so this is the correlation that we're going to use. But for the sake of completeness, what about this one? This one is the correlation that you use to try to find the average Nusselt number whenever the flow does transition to turbulence somewhere on the plate. Okay, so if there is turbulence, no matter where it is, if the Reynolds number evaluated at the edge of the plate is larger than 5 times 10 to the 5, then there will be some transition to turbulence, and then we have to use a correlation that accounts for that chunk of the plate that now has turbulent flow over it. Okay? And so usually when you're working with flat plate problems, you are choosing between one of the 4 following correlations, right? And the correlation that we're going to use now is the correlation for the average Nusselt number for laminar flow everywhere, which is this third one right here. Okay? And so we can immediately pull what that number is using the previously calculated value of the Reynolds number and the Prandtl number. And once again, don't think too hard about why this looks the way it does, because ultimately these are just empirically derived. There's no theoretical thing that says, oh, the Reynolds number has to be to the, to the square root, or that the Prandtl number has to be to the cube root, at least not in the context of this course. This is just experiment. This gets us to an answer. And the Nusselt number that you would calculate if you plug in the Prandtl number and the Reynolds number that we found before, right? That Prandtl number, or pardon me, that Nusselt number is going to be approximately 1,860.5. That's just what the algebra says. So now we have this answer. How do we get, the heat transfer rate per unit width? Well, we have still a little bit of a ways to go. We have the Nusselt number, but remember what the Nusselt number is supposed to be. The Nusselt number is supposed to be the average heat transfer coefficient multiplied by the length of the plate divided by K. Now this K, thermal conductivity, is of course the thermal conductivity of the liquid, right? This L is just the length of the plate, so the 5 meters. This H is what we're trying to look for, and then we already found this average Nusselt number, right? We just calculated it. So the next step is to find the H, and pardon me, that should be an average, is to find the average heat transfer coefficient as a function of the Nusselt number that we just found, the thermal conductivity of the oil, and the length of the plate. All right, and we know all of these things. And so what we find when we write this down pardon me, what we find is that the H bar for this system is approximately equal to 53.95 watts per meter squared Kelvin. That's my average heat transfer rate. Now, we have this number. So now we're back in familiar territory. Now we really don't have to worry too much about all of this correlation hunting that we've been doing so far. Any of the convection, weirdness about understanding flow past flat plates. We already know that this is just H. And so how do we relate the H to the heat transfer rate? Well, as a reminder, we had defined the average heat transfer coefficient such that it satisfied the following relationship. Okay? And this looks like it's kind of a problem because we don't actually know what the surface area of the plate is. We don't know the width. But what is the surface area? The surface area is just the temperature, or pardon me, the surface area is just the length times the width. So the temperature difference stays the same. The H stays the same. I guess I should put a bar over it to prevent ambiguities. And then the surface area gets deconstructed this way. And we can divide on both sides by the W to get the quantity that we actually care about, which is the heat transfer rate per unit width. And so we know this, we know this, and we know this. So we're set. All we have to do is just plug these in. And once again, this delta T is defined in such a way that you try to get the quantity that you're pulling out to be consistent with its description. So, for example, if I wanted this number to be positive, then I want to make sure that the delta T that I use is T infinity minus Ts, so that this delta T is positive too. And then this Q prime is telling me the heat transfer rate per unit width, the net heat transfer rate per unit width into the plate. Okay? If I had used a different delta T, the Q prime would be reversed, and then basically I'd have to think about, a very confusing notion of like there being a net heat transfer rate of negative whatever out of the plate, which is the same thing as a heat transfer rate of positive whatever into the plate. But anyways, if we do the algebra, what we will eventually wind up finding, once again, I'm just being very bold and skipping through it, is that we get that the answer is about 10,790 watts per meter, right? Remember, it's a heat transfer rate per unit width, so watts per meter. And this is it, right? This is the workflow associated with how you try to find heat transfer rates and heat fluxes and things like that through flow past flat plate systems. All it is following the steps that we talked about just now. You find a Prandtl number, you find a Reynolds number, you determine whether or not the flow is turbulent or not somewhere in the system. You make sure that you account for whether or not you're looking for an average or a local correlation, or whether or not you're looking for a correlation where the flow is laminar everywhere or the flow becomes turbulent somewhere over the plate, right? Based on your previous analysis of the Reynolds number. You decide which correlation you need to use from the 4 that are listed here, and then you use it to find the appropriate Nusselt number. And then you use the right expression to relate the Nusselt number to the heat transfer coefficient, solve for the heat transfer coefficient, and then everything else that you need comes from there. And so even though this is the end of the story for how we solve problems over flat plates, we're not done yet with convection, because we have to think about, for example, what happens when we consider one, flow past geometries that aren't just, flat plates. What happens if we have flow past a cylinder? And then we also have to consider what starts to happen when we are considering systems where maybe the connection between the fluid and the thermal properties is not one way, right? So sometimes we might find that actually what this flow looks like, whether or not the flow is turbulent, won't just be a function of the fluid mechanical properties. It might also be a function of these things. But we'll get there when we get there. For now, let's just keep taking a look at forced convection and seeing how we can replicate this process for flow past a cylinder.